Have you ever wondered how smartwatches and fitness trackers actually know what you're doing? Like, how does one of these things know that you're running, not just aggressively eating pastry? We built this. Genau. We built this. It's a wearable for cows. The goal is to use movement data to figure out what the cow is doing. So we're running a small edge AI directly on this device. It has to be smart enough to catch complex pattern locally while running on a tiny battery. We're going to show you how we squeeze a neural network onto a hardware this small by building a version for humans. We're breaking this whole process down into 7 steps and putting it to the test at the end of the video. We're keeping the theory visual and high level, so you don't need a computer science degree to follow along. But for the engineers watching, stick around. We'll be showing some of the codes and how it actually runs on the hardware. Step 1. Build a device that measures movement. Now usually this is where we have to start to design a new board and put all the parts on it, but we don't really need to do that. As our production board, it's already powerful enough to run the model, and it packs the Nordic BLE chip and the accelerometer we need right on the PCB. But there's a slightly logistical problem, and this form factor is designed to be installed on cow's ear, not sit on a human's wrist. So we have to hack this housing into something that I can actually wear. So one sec. So I don't know if this is gonna win any design award, but I would say probably not. But it's honest work. And you know what? I think we're gonna call this the Moop.
Daniel. There might be some wearable company that has something to say about that name, so you should probably choose a different one.
All the good names are taken.
Step 2. Collect the data. Specifically, raw movement data, which we get from sensors like an accelerometer. Tech giants like Apple or Fitbit have millions of users and the resources to run massive research studies. We have Daniel. But before he starts sweating, we need a reliable way to capture that data. So we wrote a small test firmware for the device that continuously reads the accelerometer data and just broadcasts it out via Bluetooth. To catch it, we bought a cheap NRF USB dongle and programmed it with its own custom firmware. All it does is listen for the device's specific broadcasts and spit that data out to our virtual COM port on my laptop. From there, a that simple Golang application running on the PC reads the COM port line by line and dumps the raw numbers continuously to an SQLite database. To build a model, you have to record the exact movement fingerprint for every activity you want the device eventually to recognize. For our test setup, we're focusing on 3 activities: jumping jacks, saying like and subscribe, and drinking coffee. If I want the device to know I'm doing jumping jacks, I have to do hundreds of them while the device logs the accelerometer data. Now, an AI can't just look at a continuous database stream. It needs distinct pieces of a fixed size. We slice the live sensor data into rigid 2-second segments. Here's the key difference from traditional signal processing. We don't use high-pass filters to remove gravity or algorithms to clean up the noise. We feed the raw, unmodified accelerometer values directly into the input layer. The model learns to ignore the noise on its own.
Step 3. Label the data. This is like writing the subtitles for the movement data. We have to tell the computer exactly what each squiggle represents, so it has a baseline to learn from. Big tech companies hire armies of people who sit and label data for months. In our case, since I know when I'm doing the running or any activities, I can tell the computer, hey, these specific squiggles, this is what running looks like. But for cows, we can't really bribe them to do any of these activities, such as jumping jacks. So to train the actual cow models, we have to get creative. We built this tool to sync video footage with sensor data. We basically begged our friends to play a game called Tell Us What the Cow is Doing. And you know who you are, so thank you. But when you have cameras in the barn 24/7, you capture things you didn't ask for. Engineering is a glamorous profession.
Step 4. Training the model. We take all those labeled 2-second chunks and feed them into the neural network so it can learn the patterns. For time series data like this, the standard move is to use an RNN or an LSTM, but those can be heavy on memory and compute. And since we're squeezing this onto a microcontroller, we decided to try a 1D CNN, a convolutional neural network first. It's obviously very much simplified, but think of it like this. While RNNs and LSTMs are stateful and keep some form of internal memory to remember what happened in the previous segment, CNNs are stateless. So while an RNN might understand the context like, hey, he was drinking coffee for the last 5 minutes, so he will probably still be drinking coffee in the next segment, the CNN just looks at every 2-second segment individually and completely out of context. Theoretically, that makes the CNN the weaker model. But in engineering, you don't use a cannon to kill a fly. If this dumber or stateless model is actually enough to recognize walking and jumping jacks, we save massive amount of battery power and RAM by not maintaining that complex memory. And it turns out, for rhythmic movement, it works surprisingly well. It scans the data looking for the specific geometric shapes of a jumping jacks or sipping coffee in our accelerometer data. And it does that regardless of what happened 5 seconds ago.
But wait, how are we actually going to do all this in the code? Let's look at the Jupyter notebook we used to train this. First, the script pulls in all those SQLite database we recorded and slices those continuous stream of raw XYZ accelerometer data into overlapping 2-second windows. Next, it splits those windows into training and testing sets. But here's the trick. The script uses a strict time-based split, not a random shuffle, because we're using sliding windows. Adjacent window overlaps and look almost identical. If we randomly shuffled everything, highly correlated window would end up in both training and the testing sets. It's a classic case of data leakage. The model would just be taking a test where it already memorized the answer from a split second before. Then we build the actual model architecture. We're using a super lightweight 1D convolutional neural network. Just 2 convolutional layers and some pooling. We normalize the input data, feed it in, and let it train for a couple hundred epochs. But the most crucial part for the hardware is what happens after the training. Step 5. The slim down. Neural networks, or AI, or whatever the media is calling it these days, are usually born in float 32, meaning every single number in its memory is a long, hyper-precise decimal. They're great for accuracy, but it's just way too heavy for our small hardware. To make it fit, we use a 2-stage process. First, we take the native model and run it through the TensorFlow Lite converter. This is where the tool handles the heavy lifting, automatically mapping the complex architecture into a lean and flat TensorFlow Lite file. Second, quantization. This is where we run down those 32-bit decimal into tiny 8-bit integers. It is like mapping a high-res photo into a simplified sketch. On our tiny architecture, this optimization will still save a massive amount of space. It doesn't sound like much, but it's the difference between a 7-millisecond inference and the chip just giving up and crashing. Step 6. Integration. This is where we live the comfort of Python and move it into a world of a lower level language and firmware. Most smartwatches runs on a stripped down version of a smartphone operating system and powerful processors. Our device runs on a simple BLE chip and uses Zephyr RTOS. When you're working with hardware this small, you don't have a massive library of functions. You have to manually tell the device which math operation the model needs to use. There's no point showing our exact code as it's tied to our specific hardware. But if you're trying this at home with a Nordic dev board, check out the Nordic TF Lite example. One big gotcha, the TF Lite resolver list. If your TensorFlow Lite model that you begin with uses an operator that the TensorFlow Lite doesn't support, it just won't work. So we've linked the compatible list below so you don't have to waste a week of your life like we did. It's important that data input into the model on your hardware devices matches exactly how it was trained in the Python code. In this case, 2-second chunks of raw accelerometer data. And don't forget to normalize your data using the parameter obtained from the training script. And if it all builds without hard fault or memory access violation, we can move on to the next step, the live test.
Okay, the system's now live. Our device is streaming via Bluetooth to the dongle to our PC and doing the inferencing. So Daniel, you can start with the drinking coffee activity.
Huh? Oh, okay, yeah. So, yeah.
And the model is 99% sure you're drinking coffee.
I'm not sure though. I'm drinking water, so I think we have room to improve. But how about we try some other things, you know, like, I don't know, maybe jumping jacks. This feels so wrong.
Yeah, 64%.
Maybe I'm just not doing them correctly. I don't know. My form is probably off. So you look at the stuff I'm doing for you guys. I don't know. I reckon what you guys should do is
like and subscribe.
Exactly. So the code works around a nice and clean office, but the real challenge isn't tracking one human. It's tracking 500 cows in the middle of a crowded and messy barn. Moving from a single prototype to real-world production means solving the stuff we ignored today, like waterproofing, chemical resistance, and a whole bunch of regulatory tests, and making sure a 1,000-pound cow doesn't treat the whole device like a chewing toy. But that's a story for another video. If you want to see the nightmares that comes next, then you know what to do. Stay tuned and see ya. Has it been a minute?